So actually I was told that a lot of you here will not have like access to AMD hardware already, and so what I've done is, so for the hands-on exercise I've created, so I think in the Slack channel Jhook or somebody, they might have uploaded a few files. So they are basically the trace files that I'll be using, I'll be showing here, and if you want you can follow along. And that's basically if you don't have access to AMD hardware. But through your own through your own allocations, if you have access to Crusher or any other system, and if you feel that you want to, so in the Slack channel there should be a PDF file as well. If you want to go along with those instructions, and if you want to start practicing and start doing things, feel free to do that as well. So what I want to show is the rock profiler specifically. And the example that I will be using in that, what I want to do is I want to show how I've collected the HIP and the HSA traces, and I want to visualize them inside Perfetto. And I wanted to collect the statistics, the aggregated statistics, and identify the hottest functions inside, like for my application. And the application that I used is Rock HPL. There is a GitHub link for that. You can follow along. I'll keep the slide open for now. The README contains all the information about how to build and how to run the application. And essentially what you're going to need is an MPI implementation and the ROCm stack to be able to use Rock HPL. A fun fact about Rock HPL, it's a benchmark which is based on the HPL, which is the high performance LinPack benchmark application. Obviously it uses HIP programming and it is optimized for AMD hardware. And this is actually the application, I want to say, it is very close to the actual HPL or the Rock HPL, which was used to extract the first exaflop a few weeks ago, or like a month ago. So we are very proud that we have made this Rock HPL publicly available so that people can play with it and they can see things. So on the GitHub, it's publicly available. You can just go and you can start playing with Rock HPL. So the JSON file, which I think is inside the Slack channel, if you open that, what I want you to do is go inside Perfetto, like on Google, just type Perfetto and open the tracer, and in a minute I'll follow along with you and I'll show you what I'm going to be doing with that. What I'm showing on the screen is the Perfetto website. If you want, you can actually take a look at that. So once you go to Perfetto, Perfetto is actually a Google tool which is built on Chrome tracing. So I want to say it's the big fat brother of Google tracing, and you can do really nice things inside it. So if you click on the left hand side, you'll see open trace file. So if you click on that, it's going to ask you where your trace files are. So again, from the Slack channel, download the JSON file, which should say rockhpl.mi200.json. And wow, I'm practically blind here. And basically, when you select that file, it's going to just start loading, and it's going to show you this panel. So very similar to the presentation. You'll see that there are these 3 sections here, because I've only collected the HIP trace, not the HSA trace. I didn't have enough time, and I was told pretty much at the last minute that you guys don't have access to any AMD hardware here. So again, if you expand all these sections, you'll see different threads, you'll see different, and the activity. So inside the CPU, you will see the CPU activity, which is about the HIP API calls, which are related to like memory transfers and things like that. The GPU should have like 4 threads there, and copy will have like again 2 threads. So now, using your keystrokes, WASD, say for example, I want to see what this first kernel is, right? I'm just going to hit W, and I'm going to start zooming in, right? And now if I want to pan left and right, you'll see that at the top, the more I zoom in, the window which shows what time interval I'm in, it starts contracting or expanding if I start zooming out. So you can use A and D, so A to pan left, D to pan right. And you can see that, like for example, like in the first section, the CPU HIP API, you will see that there are the initial initially there are a lot of HIP device synchronize which are called, right? But it is inside the GPU thread 0 where you will see a lot of kernel launches, and the name of the kernel is CIJ underscore AIJ underscore all of that. So now say for example, I'm interested in understanding overall statistics right here from inside Perfetto. What I can do is I can use my pointer or my cursor and I can shortlist this entire region because I think it's pretty repetitive and things like that, and I just want to see what's happening. So when I do this, it's going to open a bottom panel, and there it's going to tell me what are the different kernels which are called. So obviously you can see that the first kernel, actually the name inside Rock HPL is pretty big, so this entire row is actually just one kernel. And because I selected that window, what it is doing is inside the duration it is giving me a total duration, or like and then the average duration, and it is giving me the number of occurrences. So inside this window, this particular kernel was launched only once, but there were a lot of barrier packets, like almost 43 of them. And you can keep scrolling down and you can keep seeing like different things. And basically these time windows, when you do a total of all of this time versus the time window that you selected and you take an average, that can tell you the percentage of GPU activity, for example. So say for example, the total time that I'm seeing here, like when I add, is something like 128 seconds or something, or like 12 seconds actually, sorry, my bad, like 12 seconds. But here I'm shortlisting, sorry, I've selected probably less than that. So it will tell you that your GPU activity, like if you just take an average out of that, or like just the percentage, you can see that you have more than like 60% GPU activity. And if you want to increase that, what you should do and what you should not. So again, let's close this. Yeah. And now I want to see this first kernel like that I was saying. So when I click on the first kernel here, it will show me this flow link, which is basically telling me how is it associated with the particular CPU activity. And then again, at the bottom, I can select this up arrow because now I want to just look at the details. So so this was the average, like the duration of my kernel, and it can tell you all the other things. And because I have not collected other data like stats or like read writes and things like that, it is not showing me how much data was transferred, but essentially it should give you all that detail as well for different kernels. And oh boy, this is pretty hard. So let's try and find, sorry, I'm doing this on the fly, so please bear with me. And actually, one thing that you can also do is when you do this window selection from here to there, right? You can also do a Control F and you can search for a keyword which might be existing inside your kernel. So say for example, you know the kernel name and you just want to search for it, you can always do Control F, you can type the kernel name, and it will start highlighting it, like where it is in that particular window. So what I've not shown here, and like I said, what I did not collect was the HSA trace. HSA trace and rock traces are again more helpful, and they will be again like stacked over the other sections, the GPU sections and the CPU sections. So as long as you have this JSON file, you can just use like Perfetto or even Chrome tracing, and you can start analyzing your stack or your trace or like your GPU activity. So this was a very short demo that I thought I'll give, because a lot of you don't have access to AMD hardware right now, and probably you can't collect this trace. So is there any question about using Perfetto, or like any particular thing that you're interested in? Yeah.
Can this give anything like a roofline model or anything like that?
So not with RockProf and RockGDB. So with RockProf, obviously you can, like I said, it will not spit out a proper roofline, but when you do your custom metrics, you can identify things like your performance, like your gigaflops versus like your arithmetic intensity. So you can find that and you can plot it on your own, but it is not going to generate a roofline plot like other tools for now. Yeah. Yeah. Like RockProf is supposed to be a very basic tool, on, like I said, on top of which there are other tools that are made. So there is something called as AMD MicroProf, and AMD MicroProf is again a tool which gives you a nice graphical user interface, and it gives you all this all these plots about like the heat map, the flame map, and things like that. So there you can get a roofline, but not directly with RockProf. Yeah.
I just noticed here that like thread 0 seems a little busier than like 1 and 2, for example. Mm-hmm. Is that something to be worried? Like what's going on there?
Yeah. So thread 0, like for example, in this particular case in HPL, it is solving. HPL is basically solving random sets of linear systems, and essentially most of it is getting solved in, like in this example that I've used, it's getting solved in the default stream. So thread 0 and thread 4 are showing you different streams that are inside your GPU kernel. Like and I ran this only on one GPU with 4 streams. So that's why you're seeing that, and the default stream is doing most of the work essentially. Yeah.
Would it be like more balanced ideally, or is that not?
It really depends. Like just having multiple streams does not always mean that you can just parallelize every aspect of your application. It really depends. And again, you have limited resources on your GPU. You can create, for all you care, 100 streams, right? But you only have limited number of warps and or wavefronts and threads that can get activated. So it's really a scheduler's job to see like how you're populating each stream. So if your, for example, default stream is doing most of the work, your rest of the streams are still going to keep waiting because they don't have any resources. You can't launch any job on that, right? So it really depends on the application. Yeah. Any other question? Yeah, so whenever you get access to AMD hardware, and like through your institution or like through other places or like even on your workstation, if like the PDF that is included there, it has instructions of similar kind, how I collected this hip trace. If you get a chance, please do that. I will be available on the Slack channel, and if you have any questions, just feel free to reach out, and I'll be happy to answer them. Sounds good. All right, thank you.
Thank you.
this is kind of a combination of guided demo and walkthrough. So I shared my slides with Jay Hook, and they're really intended to be pretty self-contained exercises. So all of this work is done on the Intel Dev Cloud. So there are instructions on how to get set up. I think Jay Hook already shared those. But if you sign up for an account, you basically have free access to Intel hardware that has Intel GPU. So what this exercise does is it shows a bunch of the analysis types. It shows how to build the application that I'm going to use. So I'm just going to kind of walk through really quick. But I'll primarily focus on a demo of the results I've already collected. So if people, again, I'll be here later. If people want to kind of try to walk through, if you want to walk through yourselves, and if you run into any problems, you can come back to me and we can kind of walk through them together. So, okay. So the Dev Cloud is basically just a bunch of machines that Intel has provided. A bunch of them do have GPU, so people can just kind of try out one API. If you've ever had to go through system administration, getting your tools installed, and it's always a pain. So here you basically know everything's been tested. Everything should theoretically work. All the tools are already there, so you can just basically focus on your own application. So again, log on to the Intel Dev Cloud. There are certain commands here. I do give the setup. It's basically a standard cluster configuration if you're probably familiar with. So basically, you log on to a login node, and you basically can do nothing there because the amount of compute you can do there is very limited. So to actually git clone the stuff that I have here, you'd actually have to use this qsub command to spin up a node. I mentioned a GPU node, but some of these exercises are specific. Are CPU exercises. They really can be done on your laptop. Again, if you're familiar with Parallel Studio, one API is a little bit different. We've kind of changed philosophies where it's free. So from your perspective, you can basically download on your client system and basically have the same code that's running on your clusters. A lot of people here are running Macs. So if you wanted to, you can download the Mac pieces to your Mac and basically connect remotely to your cluster, or you could basically just run your collections and copy the directories back to your Mac and just visualize them. And that's basically what I do primarily. So again, a lot of this is reference material, getting set up with the Dev Cloud. Here are some of the steps that we're going to go through. There are basically two phases. This phase here is the CPU profiling stage, but I do go into the offload advisor piece that I talked about before. And then the second phase is the GPU analysis phase. So again, this is a kind of I would say it's a boring application because you've seen it for the last 50 years, but it's convenient and it's available. You can just git clone this in actually git clone. You can git clone all the OneAPI samples. There are dozens. So basically, it's kind of a nice setup because they do have some OpenMP code in there. They have Fortran code in there. They have all sorts of code in there. So it's a good resource. So in this particular case, we're recommending some tweaks to the standard codes that's there. I've mentioned several versions of the Intel compiler. One of them is the classic version, and the other one is the one that has offload available to it. The names are ICPC is the classic, and it's ICPX is the newer one that supports offload. Yeah, and we're not backporting any of the offload stuff to the older compiler. The reason why I'm even mentioning this is, again, this has been a shift in philosophy. All of the newer stuff going forward is LLVM based. So in case people like that direction, that's where the industry's going, pure and simple. Okay, some of the tweaks. A lot of these tweaks are, as Chris was mentioning before, I mean, these are statistical tools. So you're not getting a stream of profile. You're basically getting an interrupt-driven profile. So what that means is if your application runs too quick, it's possible that we're not going to get enough samples to actually show you anything meaningful. So what this does is basically make it so you can actually see something. Some of the commands, basically this is trivial. It's basically just make and make run. Those are the things that build this application. So here are the parts that are specific to vTune. And again, as I mentioned in the previous talk, slides are fine, but I mean, a lot of this really does demo better because you can actually see what it looks like. And that's what I'll be showing once I get through this walkthrough. But basically, when you're running vTune, the standard way of running it is either the command line that I have here, or you can create a project and basically just specify the application. Again, I tend to almost exclusively use the collecting via the command line and then just visualizing using the GUI. You can also get reports, and again, we generate CSV, we generate text. It's just not as friendly as using the GUI. The GUI is really, I think we've done a pretty nice job about just visualization. One comment I'd like to give here is, if you can see that little button there is circled. That's what we call the command line button. So sometimes you're not sure what command to give on the command line because it can be quite cryptic, and there's a lot of different options. There's a lot of different anyway. Sorry. As you can see, I'm online here. People ping me all the time. So the command line button basically gives you the exact command that will generate what you set up in the GUI. So you could basically cut and paste and just put that in a terminal window, and that should give you the exact configuration that you configured in the GUI. And again, that's purely for convenience because again, it can be quite cryptic. So at its simplest, vTune will tell you what parts of your code are hot. Obviously, when you're optimizing your code, you want to focus on the areas where you're spending the most time. So that's the command you would give to generate a hotspot report. So vTune has two different modes of hotspots. One of them is hardware-based, and the other one is software-based. They're quite different how they're implemented, but conceptually they're the same. They basically are telling you where you're spending your time. The hotspot hardware mode is I think is superior because it has greater granularity. It also allows you to profile your entire system. You don't have to specify an application. You can basically say, I want you to run on the system for 10 minutes and tell me everything that's going on. And then vTune will basically give you everything that's going on in the system, whether it's the kernel, whether it's the OS, everything. So it basically has insights into everything on the system. The software mode doesn't do that. Software is much more like a debugger, where we're inserting timers into your application and just basically getting start and stop. But that does give you a lot of tuning information. But it's, again, we consider that more algorithmic tuning rather than tuning for the individual architecture. But they all have certain properties. Software mode does give, both of them technically you can attach. You can use attach. You don't have to start from launch. You can basically attach onto the application. Hardware mode is a little. It definitely has more restrictions when it comes to that. So this is something that you can visualize better in the GUI. But one thing I wanted to highlight here is the section over here on the right that's all colored in gray is that's basically vTune trying to kind of be an expert system. It's trying to tell you what it thinks are the issues in your system. So as you can see here, there's a lot of information. It gives you what it would recommend that you do next, some information on vectorization, maybe microarchitecture usage, parallelism, and all sorts of information. But at its basic, it's giving you the top hotspots in the system. It's giving you the elapsed time. Elapsed time in vTune is wall clock time. CPU time it's almost always the case. CPU time is more than elapsed time because CPU time accumulates across all of the cores. Okay. So I've only shown you previously the collection in summary. There are also tabs at the top here. So you see the summary tab. Right now I'm showing you the bottom-up tab. You also have the caller-callee tab in the top-down tree. So bottom-up gives you how much time are you spending in your underlying functions, but it does not include the children of those functions. So for example, if your first function that you're calling is main, and then main's job is only to call 2 other functions, then the amount of time you're spending in main would probably be 0, because all it's doing is calling 2 other functions. Now, top-down is the exact opposite. So top-down, main would contain 100% of the time, and then you would cascade down through the call tree, depending upon how much time you're spending in the various pieces. So I spend most of my time in bottom-up. Caller-callee is kind of a nice feature where it gives you, if you click on a function, it tells you who called this function and who does this function call. That's kind of a nice way to kind of get the lay of the land as far as the architecture of the system. This is another kind of higher level type of analysis. We call it HPC performance characterization, kind of showing how to set it up. In this case here, what we're doing is we're running on an individual host. We're going to launch this application. The other option would be to attach to the application or just analyze the entire system. HPC performance characterization, it's going to collect some more information here. It's going to get information on the OpenMP regions. It's going to evaluate max DRAM bandwidth, and then it's going to analyze the memory bandwidths. One again, nice feature of vTune is when you run the memory analysis, you'll see a timeline graph. But the top of the y-axis is actually the maximum possible that you could achieve on that system. Because how we get that is we basically fire off micro benchmarks that will give us the maximum. So you can see relative to, how is your program doing relative to the maximum that's possible. So again, I'll show you a quick demo of this once I get through this. But basically, HPC performance characterization is basically trying to give you, are you utilizing all the cores, are you memory bound, and are you vectorized? And then once vTune tells you that, then you can start drilling down with some of the deeper dive types of analysis. And then really quickly, we'll talk about Advisor. So Advisor really is where vTune is more of a general purpose profiler. Advisor is more of a kind of a specialty kind of tool. So it really gives you the most information that you could possibly get on vectorization. But it also has some nicer features for things like roofline. And it does have we've been extending it for quite a while now. But again, it's going to have some niche areas that it does very well, where vTune is much more of a wider breadth. Advisor is almost exclusively software-based. So it doesn't access any of the performance counters that the vTune does. All of it's done through software instrumentation. So when you bring up Advisor, it's basically it presents you with what we call perspectives. So do you want to be modeling your GPU? Do you want to do GPU analysis? Those are the two areas up top. Or do you want to just focus on your CPU, your vectorization, your CPU roofline, or threading, which is the last option. Once you get all that set up, you would click on that Start button, and it would run your application. And as we mentioned before, all of this can be done exclusively using the command line. Again, one nice feature for the roofline is if you want to not use our GUI at all, if you want to just generate HTML, that's an option as well. Has anyone here used Roofline before? Just kind of show of hands. It's gotten pretty popular. Again, as you saw, NVIDIA is doing the same thing. I mean, a lot of this is coming from industry. I think we've done a pretty nice job as far as the interface is concerned. I would recommend that you give it a try. It really tends to be, I think of it as a tool that kind of lets you think of a strategy. I mean, strategically, how do you want to optimize your application? What loops and which functions, which kernels lend itself to optimization? So obviously, depending upon where you are on the y-axis, if you're already hitting the L1 bandwidth max, then there's not much you can do. That's the max. But as you can see here, depending upon whether you're on the left-hand side of the chart or the right-hand side, it's going to be, are you memory bound or are you compute bound? Or, as most applications are, you're somewhere in the middle. But again, depending upon how close you are to a roof, is going to basically give you strategically what should you do and which one should you focus on for the greater bang for your buck. Okay. So Roofline is kind of this kind of shows how Advisor is integrated into as far as the different types of perspectives. So you can basically be in your roofline perspective and showing you the roofline, but change perspectives, and all of a sudden you can get a kind of a more of a view of more of a hotspot type of view, where it's going to give you each loop, how is it vectorized and why wasn't it vectorized? What instructions were used in that loop? Are they mostly memory instructions? Are they mostly compute instructions? What type of compute instructions? Are they vectorized? Are they not vectorized? So all that is available. This is our offload advisor tool. And again, all this can be done using the command line. Okay. I want to jump ahead here a little bit. So depending upon whether you want to focus on CPU or GPU, you're going to have to go two different paths. So if you start with CPU, then the code that you're cloning is practically already there. But if you want to actually experiment with offloading to GPU, there are some changes that you need to make to the Mandelbrot code. Again, they're pretty simple. Copying Mandelbrot to offload Mandelbrot, and then making some tweaks to the syntax of the OpenMP call. So you're specifying the target offload. If you haven't done OpenMP offload, I think this will be a good experiment because it's pretty straightforward. It kind of gives you a little bit of insights. There is there's some documentation that Intel provides that really, it is kind of tailored towards Intel GPU, but a lot of the concepts are the same. If you were to Google Intel GPU optimization guide, that gives a lot of information, goes into a lot of specifics about what are the different calls in OpenMP, for example, and what do they do. So it's kind of a work in progress. As far as the Intel compiler is concerned, there are certain areas that are completely implemented, especially on the C++ side. Now the Fortran side is definitely trying to catch up. Okay, a couple more tweaks. A couple more compiler flags you need. And then, in this case here, I'm specifying a GPU roofline. If you ran GPU roofline on the previous Mandelbrot code, it wouldn't show you anything because it's running completely on the CPU. In this case here, since we've ported it to offload, we can run the GPU roofline report, create the HTML report, or we can basically create a snapshot of the results that we created, and basically that will create kind of a zip file that's all self-contained with all your sources that you can bring to your laptop and just basically use them and visualize them using our GUI. Okay. Save a little bit of time for our quick demo. Kind of goes into some of the features inside of vTune, GPU hotspots. Again, finally, our related content. Again, these slides are available to you. If you want to, we can step through some of this stuff one-on-one or with small groups, and we can go over and try to get you actually up and running. But let's go through a couple quick demos of vTune first. Okay. Oops. Oops. Okay. So in this case here, I've done a HPC analysis. This was all done in the dev cloud. As you can see, we have a platform diagram. We have our effective core utilization. As you can see, the machine I was running on had 48 cores. I'm using 15% of them. This isn't a very good application because it's not really showing anything as far as memory bound and vectorization. But we can do a kind of a deeper dive here by clicking on bottom up. Taking a look at what functions are hot. As I mentioned before, by clicking on this grouping flag, you can see all the parts of your, all possible ways of visualizing your application. So in this case here, since it is an OpenMP application, vTune exposes some of the OpenMP functionality. So if we click on OpenMP region, OpenMP barrier, so what it will do is it will give us what are all the OpenMP regions which exist in our application, which one, ranking them, which ones are the ones you should be optimizing first. It's not how much time you're spending, it's what are the greatest opportunities for optimization. Okay, let me go. This is of the hotspot collection that I specified in the original slides. As you can see, on the left-hand side, we have our high-level metrics, elapsed time, CPU time, how many instructions are retired. That's the ultimate goal of superscalar processors. They're all divided up into a pipeline. The instructions are decoded. They're passed through the pipeline, and their ultimate goal are to be retired. But again, this is probably stuff everybody knows, but what these processors do is they speculate, and they try to figure out the path you're going, but every once in a while they'll guess wrong, and all that work where they guessed wrong has to be thrown away. So the instructions that are retired are the ones that actually make it to completion. The microarchitecture usage, we can expand. CPI rate, again, is a pretty important metric. Cycles per instruction. So in general, Intel processors, it varies depending upon what processor you're on, but they can execute instructions out of order, and they can execute multiple instructions at a time. So the ideal limit would be, most of these processors can execute 4 instructions at a time. So your ideal CPI would be 0.25. In this case here, ours is 0.76. Since it's not flagged, vTune considers that pretty good, which is true because the ideal is not really possible. But I want to kind of flag on the right here all the insights that you see, all the areas that vTune considers areas that you could optimize. Those are the areas where you'd probably go next. But as we go in here, look at our bottom up. As you can see, microarchitecture usage is being flagged. Let's try expanding that. As you can see, these little carrots here at the end, we can see what does microarchitecture usage consist of. And again, I mentioned the timeline gives you quite a bit of power. As you can see, how many OpenMP threads we have. If we did have an area that we considered an area for growth, we could select the area, and zoom in and filter by selection. It really only makes sense where you're visually seeing an area that looks suspicious. If that happens, you can select that area, and then that small area becomes the area the only area that vTune is focused on. So everything expands to that, and then the top part of the screen will update, and you'll only see what was executing during that particular amount of time. Okay. Let's touch upon GPU hotspots really quick. GPU hotspots. Okay. Look at the summary first. GPU hotspots is the deepest dive that the vTune does for how much is going on in your kernel. As you can see, some of the key metrics are how much time are you stalled. So GPUs they're all pretty much the same. They're massively parallel. Some of the biggest problems they have is keeping the pipeline so that it's busy. I mean, if a lot of memory has to happen, then what will happen is the processor will stall and they'll have to wait. So in this case here, we're seeing 55.6%. Obviously, that's triggering some flags here. If we hover over that flag, as you can see, vTune has some useful information. I guess it's not that useful, but it is kind of a nice graph. Let's kind of dig down a little bit deeper. If we click on the graphics tab, oops. What's going on here? We should be, I don't have the sources set up here, it looks like. I'm going to open this again, because it was showing me that memory hierarchy diagram. Oh, I know what happened. So what happened there was I had selected a piece of the timeline, and since that piece of the timeline didn't have a diagram that it could show, it basically was saying I can't show you anything. But if we cancel that filter that I did, and then, oops, great, I got to open. I'll open up the result again. Oops. Okay. Takes a minute to load. Okay, so I kind of like this diagram. I think it gives a lot of useful information. One thing that's important to know that it is kernel specific. Since I'm selecting a particular kernel, it's going to give me the information on that kernel. If I change kernels, it's all going to update. It's only going to give me the information that's specific to what I selected. Go back to the actual kernel. As you can see, Shows our execution units, what percentages are active, stalled, idle, how many threads, in this case here, 409,000. How active is SPU utilization, and then takes you to the different levels of the memory cache, L3, GTI, and then finally the outside to the CPU, and then back to the actual CPU, and how active are the CPU cores on the system. To drill down even deeper, kind of a different way of seeing the same type of data. If we click on the Platform tab, again, we have all sorts of information here as far as what is the workspace, as far as what's global, what's local. So what is the space that we're actually talking about? The computing tasks, how much time are we spending SMD with? What are the data that's transferred for this actually to happen? And the execution array on the right-hand side, showing the percentages. Scroll across here a little bit. There's a lot more information that's here. As I mentioned in the previous talk, conceptually, the Intel version of this is basically giving similar information, but it's not presented in the exact same type of format. But conceptually, it's very, very similar. Okay, that is basically the guided demo portion. So again, if people want to do a slower walkthrough, if people want to kind of break off into individual teams, we can definitely do that later on, and I'd be happy to do that. Any questions? So somebody asked me earlier about Raja. If you come up after, I do have I can connect you to the people who are working on that at Argonne, and I can also connect you to my my teammate who's actually doing the most work on that. Please.
Probably you've said it already, but I missed it. So the Intel suite for benchmarking, like if I have a setup with an Intel CPU and a NVIDIA GPU, the GPU part doesn't really do it here, right? You cannot profile the NVIDIA GPU, can you?
You can't, right? So obviously the Intel GPU is again obviously separate piece of hardware, but the pieces of that workload that are running on CPU, you can see the CPU side of it would be visible, right?
So I have the roofline plots, say, on the dev cloud. Will I be able to visualize it remotely from the dev cloud, or should I have the Intel Advisor installed on my system?
What I would recommend for that is to use the commands to generate an HTML file and just bring that and just open it in Chrome. Or you can certainly download the Advisor to your laptop, and that's fine too. So what you can do, there's also commands for this, is once you've done the commands that you wanted to, there's a snapshot feature in Advisor that basically creates a totally packaged up version, and you just copy that back. Unfortunately, the dev cloud doesn't have any GUI functionality. All of that has to be done on your client.
So for the example that you've just shown, how would you proceed to figure out what kind of things would optimize? Like I saw a few metrics, like for instance, microarchitecture usage is 30%. Is it good or is it bad?
Right. So VTune flagged that because it basically exceeded our heuristics for being bad. So the recommendations in that case would probably be to run a microarchitecture analysis, which goes into a deep dive on microarchitecture. So that generally breaks down to several higher level metrics. For example, memory bound. That's a very high level metric, but then it cascades down to what are the pieces that make it memory bound? What level of the memory hierarchy? Is it DRAM? Is it remote DRAM? There's all sorts of things. But in general, let's see if I can open that up here. Yeah. So this is a standard result that ships with vTune. So if you just install this on Windows, it's everybody has the sample matrix that vTune ships with. So these are all the metrics that we've studied and that we consider metrics that are indicative to performance on Intel CPU. So again, back-end bound. Most HPC applications are back-end bound. Again, in my experience, memory bound, again, probably the majority, but also core bound. How much of your application is being limited to what's available on the system? I mean, so the system does have limited amount of resources. As far as how the system is architected, you only have so many ALUs. You only have so many ways of doing a float divide. And so there are limitations, and they're all specific. So, for example, if we went down to core bound, you go into this port utilization. And again, if you're not familiar with computer architecture, you wouldn't have to be. If you just hover over port utilization, it basically kind of gives you kind of a high level of what that means. But the simple explanation is these ports are where the work gets done on your processor. And if there's not enough resources, that's going to affect your computation. In this case here, it's not. In this case here, we're DRAM bound 69.2% of the time. Obviously, we're memory bound because there are other pieces that do go into this. But when it comes down to it, you're either going to be front-end bound or back-end bound. So front-end bound are basically you're trying to decode the instruction stream as it comes in, and then pass those instructions to the back end so they can actually be worked on. So there's different techniques for either one of these. So for example, if you're front-end bound, sometimes what you can do is you can kind of give the compiler some hints just so that it can place pieces of the code closer together. There are features of the Intel compiler called profile guided optimizations, because the compiler doesn't know what's important. Because basically it's static. It tries to make all these assumptions, but since it's not running your application, it doesn't really know that much. So if you can give it some hints, it can place things better. So that's basically front-end bound. Again, that's not an area that I spend that much time in. Things like batch speculation, let's kind of expand some of these things and see what they actually mean. Branch mispredict, that's probably the most common thing. If you're in a loop, for example, you're going along your merry way, and that's going to happen. If you're looping to 100, you're going to be on the same code path 100 times, but eventually you're going to break out of the loop, and so that's going to be a branch mispredict. Machine clears are a little bit different. Machine clears are basically, we get to a point where everything just has to be thrown away. So that's a machine clear. Obviously, that's going to cause some problems. If you go down to the memory bound, some of these things are pretty obvious, but L1, L2, L3, some of these things, it's nice to know how the caches are laid out in memory. How big are your caches? Are they exclusive? Are they inclusive? So Intel basically just did a major re-architecture of our cache structure. So we went from having an absolutely huge L3 that was shared amongst all the CPUs to a relatively smaller L3, but a larger L2 that was dedicated to the individual cores. So because that was driven by the applications that were being run. It was, in this case here, there were independent threads that were executing on a particular core. So in that case, you basically want that L2 cache to be as large as you can make it. The L3 cache is, again, the shared resource across all the cores. So that can run into a case where you have two threads that are trying to access the actual same piece of memory. I mean, somebody's going to write, somebody's going to read. There's going to be a contested access, and that can cause a problem. As far as optimizing something like that, so there's a concept called false sharing. So where it looks like you have a contested access, but you really don't. So although it looks conceptually, you can think of yourself as accessing a piece of memory, whether it's if you're an integer that's going to be a particular size. So, but that's not how processors work. Everything, as far as the processor is concerned, is a cache line. Okay, it's going to bring in a cache line to a level of memory, and that's basically tagged, and that's something that's tracked. So for example, if you were accessing a record, and that record could be stored with 4 pieces on a cache line, then if one thread was accessing slot 1 and the second thread was accessing slot 4, so the threads aren't really sharing anything. So, but from the processor's perspective, they are. So that's something that's going to be a contested access. It's not, that shouldn't be a contested access. So you could re-architect your memory structure so you know that memory is allocated in a way that pieces so you don't have false sharing. So you basically pad enough of your fields so that they either encompass a complete cache line, or you know that threads aren't going to run into something like this in cause a false contested access. But there's all sorts of things here. If you hover over any one of these metrics, it gives a lot of information. It gives you some tips about what to do next. Please.
Yeah, so if I see it now, then I see that it's mostly DRAM bound, right?
Yeah.
So typically we run larger simulations, and it contains different parts of the code, right? And different parts will behave differently. So I just wonder, how can I trace that back to figure out where the problem is? I get that I have to find a solution then, but I would like to understand where the problem is. Can I trace back that DRAM bound somehow to the different parts of the code that I was running?
Yeah. So DRAM bound. A lot of these things can be intrinsic to the application that you're running. I mean, sometimes you just have an application that is doing a lot of DRAM access.